let me write the best references for my talk, and they are, the first one is the Tarski number of groups by Ershov, Golan, and Sapir. The second one is the amenability and paradoxical decomposition. For pseudogroups, and discrete metric spaces. By Cheherini, Silverstein, and Kirchhoff. And P. Harp. And of course, this reference is one of the basic references for me. It is weak convergence. It's not a strong convergence for amenable groups. And the concept of configuration is coming from this reference. And I would like to review something from yesterday. We say that if G is a discrete group and G and E is a configuration pair, for G, I mean a pair of an ordered finite subset of G and a finite partition for G, where G has n elements, G1 to Gn, and E contain subsets of G, disjoint subsets that cover G. It's a partition for G. And an n+1 tuple is a configuration corresponding to this pair. And we write it belongs to CON of G and E if we have, for some element in E, C0, for each J, GJX0 belongs to E, CJ, and we have some examples. I want to recall one of them, and it was F2, the group generated by A and B, the free group, non-abelian free group on 2 elements, 2 generators, and G was the generator A and B, and E was E1 and E2 and E3 as follow. Omega A and the identity element, E2 was omega B and omega B minus 1, and E3 was omega A minus 1, and let me write them here, CON of G and E. I call them C1 to C7. They were these configurations. Let me write 1 to 1 1 2, C2 2 1 2, C3 was 2 1 1, C4 was 2 1 3, C5. This configuration 3 1 2, and C6 and C7, I write them here to be seen. C6 was 3 2 2, and the last one, C7, was 3 3 2. Okay. These are configurations corresponding to this G and that E. Let's try to find a solution for this system, the system of equations. I remind the definition of this system. EQ of G and E is this system, the system containing of these linear equations. FC, C is in CON of G and E, and C0 is I, and FC, C is a configuration, and Cj is I. Then, after writing the configuration equations, you have FC1. I remove F most of the time, just write C. C1, by this I mean FC. C1 is C1. The first one is 1, is only C1, and the second, I'm writing the second position one. It is C1 plus C2, C3, 4, 5. And for the last position one, we have only C3. For number 2, it is C2 plus C3 plus C4. And for the second one, to be 2, we have only C6. And for the last one to be 2, we have 1, 2, 5, 6, and 7. And now for 3, the first 3 is C5, 6, 7. The second one we have for 3 only C7. And for the last one to be 3, we have C4. So we have 1, 2, 3, 4, 5, 6, 7. For this one, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It means that these are, as I said, in this part says that x0 of C, this set is a partition for G. And the middle part says that x1 of C, where C is a configuration, is a partition for G, and the last one the same. So try to find the solution. It's very easy to see that the only solution is the trivial solution. FC or C is 0 for each C. Why? Because after removing C1 from this part, you have C2 plus C3, C4, C5, because we are trying to find non-zero, non-negative solution. If FC is non-negative, you can conclude that each FC is 0. Actually, something happened here. It's because the group F2 is not amenable. The reason is, in fact, we have an important theorem from a last reference that I said. Before that, I defined the normalized solution. By a normalized solution for the system, a solution FC, this is a configuration, is called a normalized solution if none of them is negative and the sum of them is 1. It means that this solution is normalized. And it is obvious that existence of normalized solution is equivalent to the existence of non-zero, non-negative solution. And it may be very familiar to most of you that working with duality and convexity and something like this. We have some theorems that will help us to find normalized solution, for example. Now the theorem is a discrete group G is amenable if and only if for each configuration pair G and E, the system has normalized solution. EQ of G and E admits a normalized solution. You can prove this easily. The one direction from left to right, for this part, it is enough to put FC to be mu of x0 of C, where mu is the finitely additive left invariant probability measure for the amenable group G. And it is very easy to see that these are all non-zero and the sum of them is 1, and also they satisfies the equations. And for the other part, Since every configuration equation has normalized solution, you can find a net converging to invariance in Weierstrass topology. F alpha, a true net F alpha in P1 of G, such that F alpha minus X F alpha tends to 0 in Weierstrass topology, and it is equivalent to the amenability of groups. Okay, so F2 is not amenable because of this theorem. On the other hand, we have another important theorem, Tarski alternative. It says that for every group, for every discrete group, one and only one of the following condition happened. Only one of the following. One, G is amenable, and two, G is paradoxical. Therefore, if G is not amenable, then G is paradoxical. About paradoxicality, we talked yesterday, discussed enough, and now it means that there exists a configuration pair such that EQ of G and E admits no normalized solution. Now, the question is, if you have these configuration equations, how can you construct a paradoxical decomposition for the group? And then how can you find an upper bound for the Tarski number of group? And we will talk about this later. Let me say something about configuration equations other than normalized solution. It says that for every amenable group, every configuration equation has normalized solution, non-negative, non-zero solutions. But look at the special case of finite group. Let G be a finitely generated finite group. Let theorem let G be a finite group. Now, just finite. Then try to find them and any G and E, an arbitrary configuration pair. Let's try to find the solution for the configuration equations for these groups. EQ of G and E, it's an arbitrary configuration pair. And as I said some minutes before, this is the FC x0 of c. This is the solution, a normalized solution for the system. But you see that we know that mu for finite group defined something like this: the cardinal number of A over the cardinal number of G, and A is now x0 of C over the cardinal number of G, and x0 is non-empty by definition, so it is strictly positive. It can't be zero, and therefore we have a theorem here, another theorem. It's very easy, it's just a lemma. The theorem says G is finite. Let G be a finitely generated now. Let G be a finitely generated group. Then G is finite if and only if for each configuration pair EQ of G and E has a strictly positive solution. One direction is clear, I explain it, and for the other direction I want to give some proof. Now, I remind something from yesterday. We say that if G yesterday I said that if G is a finitely generated group, then G is finite, G is infinite. In fact, if and only if there are subsets A and B of G equally decomposable to each other, and A is a proper subset of B. I want to use this lemma to prove the theorem. Now let G is not finite. If G is not finite, there are two subsets, A and B. Proof of the other direction. There are A and B with this property. A is a proper subset of B, and A is disjoint union of AI or some finite parts, and B is disjoint union of BI, I from 1 to n, and each AI is a multiplier of the BI for some GI. Some G1 to Gn each. Now try to find a configuration equation with no normal, with no strictly positive solution. Let G be that set, G1 to Gn, and suppose that E is this set, A1 to An, B minus A, and B complement. This set may be empty. In this case, you can remove this. It's not important for us. So it's a partition for G, and this is a string, finite string of elements of G, and therefore we can write EQ of G and D. I don't need all equations. I try to find only one of them, only some of them, and after that I prove that this system cannot have a strictly positive solution. So the equations are FC, where x0 is a subset of E1, EI in general, and FC, where xj is a subset of EI by definition. Now, I said I don't need all of them, just write I, the same number. And you see that this is applying the summation on both of the equation from 1 to n, x0. And instead of EI, we must write AI because our configuration, our partition is this special configuration. For now, I just use this parts of the partition, and we are x0 is a subset of AI is equal to from 1 to n fc, where xi is a subset of AI. And let's change them to their inverses, ga1 minus 1 to gn minus 1. So we have this. I continued it here. So we have fc x0 is a subset of AI is, by the definition of configuration equations, we have fc where x0 is a subset of bi because of this equation, and of course because of the choice of this gi. And but we know, let me rewrite it. It means that the sum of fc's where c0 of c is a subset of A is fc where x0 is a subset of B, and it is fc x0 is a subset of A plus fc where is not a subset of A. x0 is a subset of B minus A. Therefore, after removing these two, you see that the sum of fc's where x0 is a subset of B minus A must be 0, and for non-negative solutions, it must be 0. Therefore, because this set is not empty by our assumption, therefore every fc in this place must be 0, and the system does not have any strictly positive solution. And we can extend this to locally finite groups. This group was finitely generated, and I can prove this for an arbitrary group and locally finite instead of finite. It's not also difficult. I remind something from yesterday. If G is an arbitrary group, just discrete, then G is finitely, let me put some parentheses here. G is locally finite, if and only if the same. G is not locally finite if and only if there are equidecomposable subsets of G that one of them is the proper subset of the other. Okay, I try to make a discussion here, and very briefly, for this part, if G is not locally finite, then you see there are subsets of, by our remark, let me write my theorem We proved this yesterday. A new theorem says that for arbitrary group, let G be a discrete group, then the same happened. G is locally finite if and only if for each configuration pair EQ of G and E admits a strictly positive solution without assumption to be finitely generated for G. We have this theorem, and I said it's not also difficult for proof. If G is locally finite and G and E is a configuration pair, there is some set G here, finite G and finite partition E, and I want to find a strictly positive solution for this system. G is locally finite, and for each C in configuration G and E, x0 of C is not empty. Therefore, for each C, I can choose a number x C in the base point of the configuration. Because it's not empty, only one of them, choose one of them, and then name it xc. Then define H to be the group generated by G1 to Gn, where G is G1 to Gn. And also xc, where, let me write it like this, xc, where C is a configuration. This set is finite, so H is finite by the assumption. And by the previous theorem, we have, because it's finite, every system corresponding to this group has normalized solution, but the point is that here you can prove this very easily, that CON of G and E is CON of this G and some F, where F is a partition for H. You can define it, you can write it yourself, it's very easy. It is enough to write Fi to be AI with intersection by H. This is the partition for H. And they have the same configuration sets. So this is a configuration set for H. Therefore, it has a strictly positive solution by the previous theorem, and therefore this system has a strictly positive solution. AQ of G and E has a strictly positive solution. Therefore, the proof is complete, and we find another theorem for here for finite groups. You know that locally finite groups are amenable. We discussed this before. Every locally finite group is amenable. So by theorem, we know that the system has a normalized solution, but now what we prove that this solution must be strictly positive. Okay, this is a special kind of amenable group and a new theorem. Now, let's go back to Tarski numbers again. Tarski numbers is the minimal number of the pieces of paradoxical decomposition for a group, and we denote it by tau of G. Yesterday we talked about this. We say that the Tarski number of every group is always equal or greater than 4. For some cases, we have something more. For example, when G is torsion, as we say, the Tarski number of G is greater than 6 or equal. It's not very difficult, but we didn't discuss about this. And something about Burnside group, we say when this is the exponent and this is the number of generators. And the Tarski number of this group in a special case is between 14 and 6. This is because the group is torsion, trivially, and it is less than 14. And this part is complicated. You can find it in some references. And another thing that's very interesting for us is this theorem. The Tarski number of a group G is exactly 4 if and only if F2 is a subset of G, or a copy of F2 is a subset of G. This direction is obvious, but this direction is not so obvious, but using pinpoint lemma, you can prove this. And it's routine. If you know the pinpoint lemma, it is not very difficult to see. Okay. I said that there is a configuration pair where the equations has no normalized solution. If and only if G is paradoxical. Now, I want to write exactly what we want to see. And the problem is, if EQ has no normalized solution, how can we construct paradoxical decompositions? Or even more, how can we find, as I said, Tarski numbers or an estimation for the Tarski number? I try to answer this question by some examples. After that, I with some attempt, I try to answer in general. This example here for us as a non-amenable group is F2. Let again F2 be our group generated by A and B. I want to make a slight change here. Let G be this set, A and B. And E1, E omega A, EB, it depends on you to choose your partition. And this one is E2, EB, WB, omega B, and E3 be the complement of them, omega A inverse, omega B inverse, and the identity element. It is not difficult to see that the configurations corresponding to this string and that partition is this set. Configuration of G and E are when you choose your number here, multiplying by A, it is 1, 1, and by B, by 1, 1, 2. Choose your number here, it is 2, 1, 2. And if you choose your number here, you have, it can be only the identity element. In this case, you have 1, 3, 2. And different choice give us this configuration: 3, 3, 2, 3, 2, 2, and 3, 1, 3, and 3, 1, 1. And that's it. So these are configurations corresponding to this partition and that string of elements of F2. And this system does not have, the system corresponding to this does not have normalized solution. It's very easy to see because I write it very quickly. It is C1, C1, C2, C3. Call them C1, 2, 3, 4, 5, 6, and 7. You have C1 is C1, C2, C3, C6, and C5, 6, 7. And for the last part, no, it is enough for me. I don't need all of them. And for 2, we have C2 is C1. For the last position, C1, C2, C3, C4, and C5, and that's it. You can see that after removing C1, 2, 3, 6, 7 are 0, and here 1, 3, 4, 5 are 0, and therefore the only solution here is trivial. This system does not have any normalized solution, any non-negative solution, and I try to find a paradoxical decomposition for this system. Before that, I use some notations. I write Aij for this set, the set of all configurations in CON of G and E, for which Xj of C is a subset of AI. Therefore, you can see very easily that the union of X zeros where C is in Aij is the union of X zeros where C is in Aik, for example, and by this multiplier G K Gj minus 1. This is not very difficult to see because the union of these is exactly AI, and for the other the same happened, and maybe have this. This is the key point for us to find paradoxical decomposition. I write, for example, for this example here, and after that I try to extend this notion for unknown groups. Okay. By this equation, we have A1 0 is only C1, and A11 is C1, 2, 3, 6, 7. Okay, and for the second one, we have A20, no, for 20 is only C2, and A22 this time because I write the last position for the second equation. A22 is C1, 2, 3, 4, 5. And as you see, by this key point, we have x0 of C is disjoint union of x0 of C, where C is here, C is C1, C2, C6, and C7, and x0 of C2 is the disjoint union of x0s, where C is 1, 2, 3, 4, 5. And finally, we have the paradoxical decomposition. Because you see, x0, you can write here. I'm sorry, I forget something. It is A by this multiplier, and this is B. Because of 2 and A here, we have A here and B here, the elements of G. So we know that G is disjoint union of x0s, where C is every configuration. C1, C is 1, 2, 2, 7. Therefore, it is A minus 1 x0 of C1. It makes 1, 2, 6, 7, and plus the identity element, and x0 of the rest of them is 3, 5, and 4. C3, C4, and C5. Okay, and for the other one, again, G is B minus 1 x0 of C2, and again the identity element, x0 of the rest of them is 6 and 5, C6, and 7 and 6. Sorry, it's a complete paradoxical decomposition for G, because we have we use 1, 2, 3, 4, 5, 6, 7, and 2 times we have G. We use 1 time G and produce 2 copies of G, 2 identical copies of G, and it's the paradoxical decomposition for the group. Now, for the Tarski number, you see that this is 1, 2, 3, 4 parts. And we again see the Tarski number of F2, as we know, is again less than 4, and it's exactly 4. We know about this group, and we know that the Tarski number of F2 is 4. But in general, you may not familiar with a group that the configurations are given to you. Look at this example. I would like to write something here. Let G be a group, an unknown group. This is an example. It's a different example. Let G be a group, and for some G and E, we have, for some G and E, we have CON of G and E is configuration pair corresponding to for G, and this is configurations corresponding to the pair, like this, something 1, 2, 3, 2. It means that G has 3 elements, G1, G2, G3, because it's 4 tuple, 1, 2, 3, 2, and 1, 3, 1, 3, 2, 1, 2, 2, and 3, 3, 1, 2, and finally it is 3, 3, 2, 1. Does this system have a normalized solution, the system corresponding to these configurations? I try to write it. C1 is C1 plus C2 is C3 and C4, and the third one is C2 and C4, and for the last one to be 1, we have only C5. 3 equations here, 1, 2, 3 for the first one, second one, third one, and the last one. Now for 2, we have C3, call them C1, 2, 3, 4, and 5. So we have C3 is the second one to be 2 is C1 only, and the third one to be 2. The third one is C3 and C5. And for the last one to be 2, we have C1, 3, and 4. Now for 3, we have C4 and C5. And here for 3, for the second one, we have C2 and C4. For the second one to be 3. To be 1, for the second part to be 1, we have C3 and C4, and now we have for 2, for 3, we have C2 plus C4. Let me check it once again. For the second one to be 1, we have C1 We have C3. No, we don't have C4 here, I think. Okay. At the end, I again check it because it's very important to be precise. And for the second to be 3, we have C2 and C4 and C5. For the third one, C1 only. And for the last one to be 3, we have C2 only. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And here 1, 2, 3, 4, 5. And that's it. 1, 2, 3, 4, 5, and it's correct. So this system, again, does not have solution because by this equation, we have C3 and C4 to be vanished. After vanishing C3, we have C5 and C1 is 0. And after that, everyone is 0. The only solution here is the trivial solution. So this system does not have any non-negative, non-zero solutions. Now try to find the paradoxical decomposition or a bond for the Tarski number of the group. I again say that we don't in fact know the group. It's not important for us which group in the backstage. We only want to write the Tarski number of the or the paradoxical decomposition corresponding to this system. Now look at this. Let me write it from my note. We have x0 of C3. I use this equation, 3 to 1 and 2, 1 to 3 and 5. This one, 2 for 2 and this one. I use this one, and 3 to 3 and 5. Again, this one, this 1 to the third one, and C5 to C3, 5 and 3, this one, and I write it here. Look at this. I don't want to write the AIJ. After that, I explain it, but look at this diagram. C3 can produce C1 and C2 by this equation. C1 is C3 and C5. Okay. C2 can make C4 and C5. Now C3 can make C3 and C5. C5 can go to C3. Again, C5 can go to C3. And C3 make C1 and C2. Okay. In the last example of us, we have X C1 could make everything except for C4 and C5. And C2 by itself could make everything except for C6 and C7. And the point in that example was that these two sets are disjoint. X0 of C1 and X0 of C2 are disjoint. And you know the disjointness in the paradoxical decomposition is very important. And we cannot omit the disjointness of the sets. Recall a paradoxical decomposition for G, as I said, something like this. Disjoint subsets made the whole, not the whole, it's equal to, it is enough to be a subset of G. But we cannot omit the disjointness. They must be disjoint. And these sets must cover, as you know, the whole G, and they not be disjoint necessarily. Hj, for example, Bj, but disjointness cannot be omitted. For this example, we don't know any special problem because these two sets are disjoint. But for the current example, we have some problems. To achieve the paradoxical decomposition, I use 2 times C5 and 3 times C3. These are not disjoint. And how can we construct a paradoxical decomposition? Let me glue some of these equations, some diagrams to each other. And finally, we can see disjoint sets that make our paradoxical decomposition. I start with C3. We can go to C1 and C2 by the first equation. C1 can go to C3 and C5. C2 goes to C4 and C5. For this, we have C3 and C5. And by this, we have C3. I'm using them. And after that, C1 and C2. It means that you have only one piece of the X0 of C's per cover G. What does this diagram mean? It means that you can divide the X0 of C3 in 1, 2, 3, 4, 5, 6 pieces, many pieces, I can count them, to make the paradoxical decomposition. And let me use some color to see. One path here, we can make this only one set as a one set, and here you have another path, and you are constructing X0 of C5. Now after that, use this. We are C4, and using this path, we can go to, this is ones, C1 and C2. And here I say that count these colors, 1, 2, 3, and you see 1, 2, 3, 4. And the Tarski number, and we have another 3. by identity, it can go to itself. Therefore, the Tarski number of this group, tau of G, is equal or less than, let me count it again, 1, 2, 3, 4, and 5. The Tarski number of this group is less than 5. I don't know the group. I only know the configuration of groups. And this group is not very easy to achieve the Tarski number. But using the equations, I could find an upper bound for the Tarski number. I don't know, is there any group with this set of configurations? But if there is, I can find an upper bound, a good upper bound for the Tarski number. For example, if there is such a group, and we know that it does not contain a copy of F2, we have that Tarski number of group must be 5 because it is greater than 4, and if it is not 4, it must be 5, for example. Okay. I think we can stop here, and after that. C5 is C3, and C5. Okay, we had these two examples, and what is the common point between these two examples that we can write the paradoxical decomposition? It is this. Look at the first row, and after that the second row. We have here 1C1, and in the second row we have 2C1. Then we have 1C3, 2, and 3, and in the second line we have C3, 1, 2, 3 here, and 4, 3 here, 1, 2, 3, and 4. And for C5 we have 2C5 here and 3C5 here. Again we have 1C2 here and 2C2s here. What we do have is that C1 plus C2 plus 2C2s, and no, just 1C2, okay, and 3C3 and 1C4, I think 2C5, 1, 2, 5, 7, yeah, and what we have is 2C2s, 4C3s, and C4 is 5. Yeah, 2C5s, and we have only one C4 and 3C5. Yeah, 1, 2, 3, and yeah. This equation leads us to the trivial solution. Fc is 0 for each c. And you see, everything that you see here in the first row can be appear once more in the second row, and C4 that is not appear in the first row just once. You can see this, and it means that there is a set A here which can make itself and the whole configuration of G and E. There are all configurations here in this side, and A again, because 1, 2, 3, 5 are appear here, and also in the other side of the equation. And the point is here, is that, and for these equations, we have C1 and C2, sorry, in the first row, and in the second row, we have 2C1, 2C2, 2C3, I write it here, C3 plus C3, I write it in this shape, and the other one once, C4, C5, right? 1, 2, 3, 4, 5. And it leads to the trivial solution for the system. It is again mean that this set C1 and C2 make itself plus the whole configurations. And then we can write the paradoxical decomposition. It is enough to add the other configurations here. So we have 2 copies of the configurations. And it is the paradoxical decomposition. So the note, the main point is here. And something happened here is that we have 2 C3s here, and it's not important. In the first session, the last session, I said that, and you know that G must be only cover, but GI, AI. It's not important to be disjoint or not, and it means that it is not disjoint. 2 times you have C3. But again, the main problem, the main difference between 2 examples is that these are not disjoint, but they are disjoint. And we make them disjoint to find the paradoxical decomposition. Let's go to another example. Again, I don't care what the group is. I just write the configuration equations here. Let G be a group. A discrete group. And I write it something, I don't want to have the all equations. I just write some of them. An EQ of G and E only contains the following equations. I note that configuration of G and E is consists of 3 configurations. 5 configurations. I don't know what these configuration are. I just know that the configurations are like this. C1, some of them, not all of them. C1 plus C2 plus C3 is C1 to 1, 3, 4. Two, 3 is 2, 3, 4, 4, and 1, 3, 4 is 1, 2, 3, 5, and C2 plus C3 plus C4 is 1, 2, 3, 5 again. Okay. 1, 2, 3, 5, 1, 2, 3, 5, 1, 2, 3, 5. Here, let me check it again. 1, 3, 4, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 5, and 1, 2, 3, 5. Okay. 1. And another thing, 2 and 3, 1, 3, 4, and this. Something like this again. These are only hypothetical. I want to finally find a way to find the Tarski number in general. It's only hypothetical. Look at these equations. We have, for example, 1 C1, 2, 3 here, and this part 1, 2, 3, 4 C1. And for C2, I have 1, 2, 3 here, and I must have 4 C2s here. 1, 2, 3, and here I have 1, 2, 3, 4, and so on. You can see easily that the only solution is trivial. For example, for C3, let me check 1, 2, 3, 4, and here 1, 2, 3, 4, 5, and so on. This system does not have any normalized solution. Try to find the Tarski number for this group with this kind of configuration equations. Let me write them. We have, for example, I want to use some of them. 1 and 5 together. See, I omit C again. Not F, not C, just I write the numbers because of convenience. 1 and 5 goes to 1, 2, 3, and 4. Okay, it's because of the last one. 1, 2, 3, and 4. Maybe I must check it again. So let me write after that, because it is important for us. 1, 2, 3 is 1, 2, 3, 5. And here 2 and 3. I want to make it more complicated. 2, 3 goes to 2, 3, 4. 2, 3, 4 goes to 1, 2, 3, 5. 1, 2, 3, 5. And the last one says that 1, 2, 3 goes to 1, 3, 4. Just let me check this one. 1, 3, 4. 1, 5 goes to 1, 2, 3, 4. 1 and 5 goes to 1, 2, 3, 4. We have 1, 2, 3, 1, 2 fours here, and must have 3 fours here. 1, 2, 1, 3. It's correct. It must be 4. Okay. Again, we can construct the paradoxical decomposition because it has only the trivial solution. And you see, for example, 3, 1 in the first row and 4, 1 in the second row, and the other. So we can, by that explanation, we have the paradoxical decomposition for the group. But the point is that these sets are not disjoint. And the problem is to find a good substitution for this with disjoint subsets. How can we do this? Let me again draw the diagram. It's important with which one you should start. So let's get in here and draw the diagram. I start with the second equation, or no, by the first. We have 1, 5. Please note. We go to 2, 3, 4, and 1. These two sets have 1 in common, and I should omit this one. So I try to find 1 here in the second row of the first equation. So I have 3, 4, and I borrow 1 from the second row of this one. Therefore, 1, 3, 4 make 1, 2, 3, 5. 1, 2, 3, 5. Okay. And let's go to 2 and 3. 3 is again common with this set. So I write just 2 and borrow 3 from the second row of the second equation. Okay, we have by 2, 2, 3, 4. And the others, we have 2, 3, 4, and 2, 3, 4 is common with these two sets. So 2, 3, 4 is here. I don't need to write it again. Just the second row is 1, 2, 3, and 5. Okay. And 1, 2, 3 is here. And we can write. We don't have enough space here, but it's not. It does not make a problem. It's 1, 3, 4. So we start with these disjoint sets. 1, 2, 3, 4, and 5. And what we obtain is that 1, 2, 3, 4 here, and 5 here. So we have 1, 2, 3, 4, 5 once, and once more we have 1, 2, 3, 4, and 5. It means that using one set of configurations, we can achieve 2 copies of configurations. It's a bit complicated to write the paradoxical decomposition. It is, of course, possible, but it's not very easy to write. You must divide these sets into different parts, and after that, you can write the paradoxical decomposition and also the Tarski number of group. Okay. Now try to find the upper bound for the Tarski number of group. Just count the number of paths. This is a path here. I just count it one time. It is 1. This one is 2. This one is 3, 4, and finally we have the Tarski number of group is equal or less than, in this example, 10. For seeing this, let me rewrite the system again to be clear. It is something like this. 1, 5, make one piece. After that, another piece here. 3, 4, with this one, makes something here, and after that, something here. And this together with 2 makes the complete paradoxical decomposition. It here and here and here. So after counting the paths, you have 1, 2, till now 2, but after that 3, this one, and for this one it's 4, and for this one it is 1 here, 5, 6, and 4, 1. This one 7, and by this one it is, till now we have 7, and this one is 1 and 2. The whole of them is 9, and the Tarski number of the group is less or equal than 9. We don't need another part, so 10 is large. It is enough to be 9. So the Tarski number of this group is less than 9, equal or less than 9. Okay? But it is not the best upper bound for our Tarski number. I can make it even better. I want to erase this and I write it again. I can make it even better by use another diagram. Look at this. This example. I start with 1, 3, 4. I erase it, but no problem, you have it. 1, 3, 4. By this, you can go to 1, 5, and 2, 3. By 1 and 5, you go to 4, and 1, 2, 3. By this, you go to 2, 3, 4. And after that, you go to 1, 3, 4. And by this, you go to 1, 2, 3, 5. Now, you see, you can find a better upper bound for the Tarski number. Just using 1, 3, 4, you have one path here, 2, and 3. So, and the other one is here. So the Tarski number of group is less than 4, and therefore, if there exists such a group, its Tarski number must be 4. These are 2 and 5 that by identity go to themselves. themselves. So the Tarski number of this group is 4. You must find the best diagram for achieving the best upper bound for the Tarski number. I can give you some exercise, and you find the best upper bound for the Tarski number of this hypothetical group, and we can discuss about this tomorrow. Let me see if there exists any exercise. Suppose that there is a group with these configuration equations. It is, for example, C1 plus C3 is C1, 2, 3, 5. And 1, 2, 3, 1, 2, 5, 1, 2, 4, sorry, is 1, 2, 4 is 1, 3, 4. Um, 1, 3, 5 is 1, 2, 3, 6. And the last one is C1 plus C3 is 1, 2, 3, 4, 6. Let's check the solution. Is there any non-negative solution, non-negative, non-zero? Let me see. The first equation says that C2 and C5 are 0. 1 and 5, sorry, 2 and 5 are 0. And this one says that C2 is 0 again. And for this one, we have 2, 4, and 6 are 0. And it's your exercise. Check it if it admits only trivial solution. Try to find the best upper bound for the Tarski number of the hypothetical group that is in the back stage of these equations. So it contains 6 equations. So try to find the, and if you can, find the paradoxical decomposition, not only the Tarski number, also paradoxical decomposition. So both of them are important for us. Okay. You can, let me first check, I must be sure about the solution. After that, I write my email. My Yahoo email. You can send your solution if you can. I will check it. I will check, and after that I will answer you. Just let me see. Let me, and 1, 2, 3, 4. 1, 2, 3, 4. I think something is wrong here. Let me correct it. 1, 2. And for 3, we have 1, 2, 3, and must have 4, 3. And for 5, for 2, we have only 1, 2 here, and at least 2 here. Okay, and one of them can be omitted. C2, C3, we have 3, and here we have 4. It's correct. For 5, no problem. And for, I think, one of them can be omitted. Sorry for that, but omit this one. And I think this set, this configuration equations has no non-negative solution. This is because 1, 2, 4, 6 are 0. 1, 2, 4, 0, then C5 is 0, and so on. You can see that this equation has no normalized solution. Now, let me just say something about the question that yesterday I posed. It was that, is there any infinite group that for each G and D of G, there exists a finite group such that C1 of G and E is a configuration for F. And it is not correct. I want to answer this negatively. And it's because the theorem, we proved this in the beginning of our session today. We say that a group G is finite if and only if for each G and E, EQ G and E has a strictly positive solution. And it is impossible because if your G is infinite, there exists a configuration such that configuration pairs such that the equations has no normalized solution, has no strictly positive solution, and it can't be a configuration in a configuration set of finite groups. And because we proved this, that yeah, and for the proof of this, it's not completely my argumentation. It's somehow some discussion in Math Over Fellow and one of my colleagues together, and finally we answered this question in the negative case. So I think there is not any special thing for this session, and we can continue tomorrow.